All right, so for today's lesson, we're going to be doing an introduction into inverse functions. And basically, when you're talking about an inverse function, you kind of got to think back to when you were solving equations. So when you were solving an equation, if you had addition, then the inverse operation was subtraction. If you had subtraction, then the inverse operation was addition. And then, if you have multiplication, the inverse is division. And then if you have division, the inverse is multiplication. So that opposite operations is still going to be applied here when we start talking about inverse functions. So when we look at it, given just the standard linear function here, we say that x was multiplied by 2 to get 2x, and then we add 3 to get 2x plus 3. Well, the inverse of that, so instead of multiplying by 2, I would divide by 2. Instead of adding 3, I would subtract by 3. And we are going to do this algebraically with the actual equations, but not for this lesson. For this lesson, we're really going to be looking at all the key features of them. So first thing that is the most important is when you have a function and then you have its inverse, the domain and range are opposite. There's a reason for that, because when you solve for a function and you find the inverse, you're actually flipping that x and y value, which means you're flipping the domain and the range. All right, so notation. So when I talk about an inverse, you're going to be looking at that -1. That -1 is not an exponent. That is simply a notation, a symbol that means inverse. So when I read this, this is f inverse of x. So f inverse of x. All right, and the last thing, and the one that is really going to be helpful in determining, is when you have a function and you have its inverse, it will have a reflection over the line y equals x. So let's look at it graphically for a second. So if I have the line y equals x, let's say that I start with the function y equals x squared. Well, the inverse of x squared is going to be the square root. Now, I'm going to have to be very mindful of this, and I'm going to have to do the plus and the minus. So I'm going to do the plus and the minus because remember, when you take the square root, there's a positive and a negative. And I can see, and I'm going to turn this one into green so it all kind of flows together. But if you look right here, I'm going to kind of zoom in. They are a reflection over that red line, y equals x. Now, we are going to be looking at this graphically, and I can even look at a couple of other options. So let's say that I have y equals x to the third power. Okay, so I have x to the third power, and then that means I'm going to take the cube root. So if I'm going to take the cube root, let me go grab that root option. 3, and we're going to take, if we have x cubed, then the cube root of that, you can see that there is a reflection over that line, y equals x. And I'm going to change that to a different color so we can see it. Okay, so just keep that in mind. That is definitely going to be a way to verify some things. But now what we're going to do is we're going to look at some examples of inverses in all multiple formats. So what happens if I give you just a set of points and I ask you to find the inverse? Well, the inverse means that I'm going to flip my x and my y. It is simple as that. So if I start with my problem, I'm going to have a new set. So if my original point was -3, 4, then my new point is going to be 4, -3. Then if I had -2, 7, it's now going to be 7, -2. And then the last one is going to be 4, 0. Now the question is the inverse a function? So remember, to be a function, it means there cannot have any repeating x values. So my original was a function. All right, so I had -3, -2, and 0. Those did not repeat. However, my inverse is not a function because it has repeating x values now. They were originally the y values, but they're not anymore. They have now flipped because they're the inverse, and this one is not a function. So sometimes you can have a function and take the inverse, and the inverse may not be a function. Okay, so if I look at this on my set option, I can say that I had -3, 4, and then I had -2, 7, And the last one was 0, 4. Now I'm going to change these so they're all in blue. And we can see that these are all grouped together. All right. Now I'm going to look at my inverses that I did. So we did 4, negative 3. Let's change that to red. No, let's do green. And then we have 7, negative 2. And the last one is going to be a 4, 0. And you should be able to see there that those are reflections of each other. I can see that this point at 0, 4 and 4, 0 are reflections over that line y equals x. All right, so then the next one, it says, which of the following tables gives the values for the inverse? And I know we're talking about the inverse because it has that negative 1. If the original function, f of x, is the square root of x minus 2. All right, so I have the square root of x minus 2. So they want to know which table represents that. Well, let's find a table or let's list some values in my table and let's actually put those together. All right, so if I look at this, I have the point 2, 0. And remember, this is my original table. All right, so we're going to continue to look for some perfect points here. So as I'm moving, I see that I have the 2, 0. And then I can kind of keep looking for those perfect points. I do see that I should have one at, we'll say 3, what was it? 3, 1. But how do we make sure of this? So like I can actually turn my table option on in Desmos. So I'm going to click into the row of the function. I'm going to hit the gear button and I'm going to hit table. Now, it's going to say a whole lot of undefined because we didn't go any lower than 2. But you can change these options. So if I want to see what value of 3, then I can plug in 3, and we can clearly see that it gave me 1. I could plug in 4. So 4 doesn't give me a nice number, so I'm going to keep going. Then I can look at 5, but you can see that which ones are kind of crossing right where you would want them to at a perfect point. So we have 6 and 2. But why do we do this? We did this because now that we have our original function table, we can find our inverse. So remember, our inverse is what happens when we flip those values around. So if I had 2, 0, it's now going to be 0, 2. If I had 3, 1, it's now going to be 1, 3. If I had 6, 2, it's going to be 2, 6. So comparing this, I can see that the answer is A. All right, or we could do a mapping situation. So again, if I'm looking at my map here, I would make my original table. So I have a table here where 3 maps to negative 1, 0 maps to 0, negative 3 also maps to 0, and negative 6 maps to negative 2. So if I want to find the inverse, then my inverse, I'm going to flip my x and my y values. So my inverse is now going to be negative 1, 3, 0, 0, 0, negative 3, and 2, negative 6. So tables are pretty easy to deal with just because they're very easy to flip the values or just looking at the points. All right, so what happens if I give you a function and I ask you to verify which one of these is the inverse? So again, you're going to use some of those same skills. I'm going to look at the original. So I have y equals negative x cubed, and I'm going to use Desmos for that. And I can see that I have this original function. Now, they're asking me for the inverse. Do not confuse that with the original function. They gave us the original function. We're looking for the inverse function. So how can I verify? Well, I can find a table of values for the original. So that original table, I should be able to clearly see what points I have along my graph. I could, once again, make a table out of that, and it can give me some values. So I have negative 2, negative 4. I have negative 1, negative 5, 0, 0, 1, 5, and 2, 4. So my inverse here would be negative 4, negative 2, negative 5, negative 1, 0, 0, 5, 1, 4, 2. However, if I'm looking at this, I should be able to look at the graph that is going to look like it's a reflection over that. So we know A is not the inverse because it's not a reflection. It looks like the original. I can clearly see that C is not going to be because that one doesn't have the same shape. So which one of these is going to have that reflection value? So I'm going to start. So I have negative 4, negative 2. So if I go to B and I go to negative 4, negative 2, I do have a point there. Then I have negative 5, negative 1, 0, 0. Then I'm going to check 5, 1. And then I have 4, positive 2. And those points do fall there. So would D work? So if I go to negative 4, negative 2, that does not fall in that graph. So the answer here is going to be B. It's all about being able to identify the original values and then flipping those X and Y values, that domain and that range. All right, for number 5, given the original function g of x, find the inverse of negative 2. Now, this is one of those things that is super easy, but I find that students make very simple mistakes when it comes to this. So let me remind you that when you're looking at the original, remember we flip the x and the y. So when you're looking at your inverse, you're actually looking at the y value being input into the inverse, okay, of the original. So if I look at my inverse table, so I'm going to flip those values. So this is going to be negative 16, negative 2, negative 2, negative 1, 0, 0, 2, 1, and 16, 2. And it really is just about identifying. So for the inverse, this is going to be my input value. So my input value is 2, and that corresponds with negative 1. So the answer here is negative 1. Most times students will just go straight to the original g function, and they'll say, oh, I have negative 2, so the answer is negative 16. You have to look at the inverse value of that, okay? Very simple problem here. If I'm given this point of a function f of x, then which of the following points represents the function with the inverse? So the inverse of that value. So remember, we just flip our x and y. So this becomes negative 1, 5. Now, the domain and range of the inverse. So this can be as easy as you want it to be or as hard as you want it to be. I prefer to make things as easy as possible. So when we're talking about the domain and range of the inverse, so let me remind you that the domain and range are flipped from the original. So if I can find the domain and range of the original, then I know the domain and range of the inverse. I just flip them around. So given this original function, if I put this into Desmos and I graph, I should be able to determine my domain and range here. So I'm going to find the domain and range of my original. All right, so my domain of the original is from negative infinity to infinity of my original function. And then my range is going from negative infinity and it goes up to positive 2. So what do I do if I want to find my domain of my inverse and my range of my inverse? Well, they literally are going to flip. Your domain and your range were the opposite values of the original. So my domain of my inverse is now going to be negative infinity to 2. And my range is going to be negative infinity to infinity. So if you can find your domain and range of the inverse, then you know that it's the opposite with the, or found the domain and range of the original, then it's the opposite for the inverse. So they asked us to find the domain of the inverse. So the domain of the inverse is negative infinity to 2, which was the range of the original function. All right, so same thing for this problem. If I look at my original, I have the square root of 5x plus 10. And we're going to look and we're going to state the domain and range. So the domain is starting at negative 2 and it's going to infinity. The range is starting at 0 and going to infinity. Now remember, we want to find the domain and range of the inverse. So the domain and range of the inverse is going to be the opposite. So whatever the domain was of the original is now the range of the inverse. Whatever the range was of the original is now the domain of the inverse. So this is going to become 0 to infinity for the domain of the inverse, and then we're going to have negative 2 to infinity for the range of the inverse. And they asked us to find the range of the inverse, so it's going to be negative 2 to infinity. And again, this will make, you will be able to make more connections once we start looking at the actual equations and algebraic method of finding those. All right, so I think this is our last problem. So it says if f of 2 equals negative 3, then what's the f inverse of f of 2? All right, so let's think about this for a second. So if I have f of 2, that means that this is my x and this is my y. So in my table of my original, I have a 2 and a negative 3. Now, if I find the inverse of that, so I'm going to change my y. I'm going to make that f of x, because we know f of x, same thing as y. If I do this and I make it my inverse table, that means that this is going to be negative 3 and 2. So let's break this down piece by piece. So if I find f of 2, we know f of 2 equals negative 3. Well, then we know that the inverse of negative 3 is going to be the same thing. So it's going to be 2, because we're going to be looking at a different table. So we started by looking at the 2 to negative 3, and then we did the inverse of that, which means we're going to go backwards, and we're going to wind up back at 2 for our final answer. Now, if you have any questions about inverses, please let me know. There is a Delta Math on graphing. The graphing version, you're going to plot those points like we did for number 4. Make a table of values and plot the points of the inverse. And then there's going to be a practice on inverses through Canvas.